Welcome to this visual walkthrough. Today, we're tackling something that a lot of people dread as just abstract math, hypothesis testing. But here's the thing, it's actually a fantastic, highly practical toolkit for making concrete decisions when you're faced with real-world uncertainty. We're going to build a rock-solid understanding of Chapter 10 using these visuals, so let's just dive right in.
Here's our roadmap for this explainer. We'll start with the foundational concepts, look at error types and p-values, test expected values, compare groups, dive into chi-square tests, and finally wrap up with how this all works as a practical decision-making tool. Let's kick things off with Part 1, the foundations of hypothesis testing.
The very first question we have to ask ourselves is, what are we actually trying to prove here? To really get hypothesis testing, we need to put the complex formulas on hold for a second and just focus on the intuitive, everyday logic driving the whole thing. And that brings us to the absolute core of the issue. We always operate with two hypotheses. The null hypothesis, or H0, is our starting point, usually just the status quo. The alternative hypothesis, HA, well, that's what we're actually hoping to prove. The really interesting part here is that we aren't trying to prove H0 is right. Instead, we're gathering data to show that H0 is highly likely to be wrong. If we can do that, we're logically left with the alternative hypothesis as the only conclusion standing. So, how do we pull this off in practice? This lays out a dead simple 5-step workflow. First, we set up our hypotheses. Then, we pick the right test. Third, we check our data to make sure it meets the requirements. Next, we calculate what's called a p-value. And finally, we draw our conclusion. And remember, in today's world, software handles all the heavy lifting for step 4. Our job is just to feed the machine correctly and completely understand the logic behind the output.
Moving right into Part 2, error types and p-values. Basically, what happens when we get it wrong? To really wrap your head around this, think of hypothesis testing like a courtroom trial. We assume a person is innocent until proven guilty. That is our null hypothesis, H0. Now, if we convict an innocent person, we commit a type 1 error. That is an incredibly serious mistake. On the flip side, if we lack evidence and let a guilty person walk, that's a type 2 error. Our entire statistical system is essentially rigged to protect the null hypothesis and keep the chances of making a type 1 error as absolutely low as possible. So how exactly do we measure if our evidence is strong enough? We use the p-value. If you look at that little marked tail way over on the right side of the distribution, that represents our p-value. Put simply, it's the probability of getting data this extreme or even more extreme if the status quo, the null hypothesis, was actually still true. A tiny p-value basically means our observations are extremely unlikely if nothing has changed.
That leads us to the absolute most crucial point, the golden rule of decision-making. If the p-value is less than or equal to our pre-chosen significance level, which we call alpha, we reject the null hypothesis. We usually set this alpha level at 5%, but let's be totally clear about one thing. 5% is not some magical law of nature, it's just a practical compromise. It means we accept that, on average, we'll be wrong 1 out of 20 times when we claim to have found a meaningful change. It caps our risk of a type 1 error at a level we can actually tolerate in the real world.
All right, Part 3, testing expected values. Let's look at analyzing specific samples.
The very first and maybe most common tool in our kit is the t-test for expected values. Imagine you want to figure out if the average production time at a factory has changed after bringing in a new process. You've got data from a small sample, but you don't know the standard deviation of the entire massive population. That's when the t-test is your go-to tool, assuming the times are somewhat normally distributed. It helps you figure out if the time saved in your sample is big enough to safely conclude that the whole production line has actually gotten faster.
But what if we aren't measuring an average time or weight, and instead we're just counting successes and failures? Say we want to know if a new ad campaign is generating a higher click-through rate than normal. For that, we use a test for binomial variables. This is your perfect tool for crystal clear yes or no scenarios, and it works brilliantly as long as we have enough data, which usually means we expect at least 5 successes and 5 failures in our sample.
Moving on to Part 4. Comparing groups, pitting two groups against each other. Now, we can pull out the t-test again, but this time adapted for 2 samples. It's fantastic for comparing the averages between, say, Group A and Group B, but it still requires the data to behave nicely and follow a normal distribution. So, what on earth do we do if our data is extremely skewed, which happens all the time with things like salary data or housing prices? Well then, we pivot to Wilcoxon's distribution-free test.
Wilcoxon literally doesn't care how your data is distributed, which makes it an incredibly robust tool when you're dealing with messy, real-world numbers.
Let's look at how dead simple this is in practice today. On the left side, we've got two groups tested against each other, and the software spits out a p-value of over 35%. That is massive. There is absolutely no way we can reject the null hypothesis there. We don't have a shred of evidence for any difference. But check out the output on the right. Same software, new data, and bam! The p-value is a tiny 0.1%. That's way, way below our usual alpha limit. Here we have every reason to confidently conclude that there's a real, statistically significant difference between those two groups.
Part 5. Chi-square tests and independence.
The first variation we'll look at here is the chi-square test for probabilities. Picture a national political poll. You have an established model saying Party A should have 30% of the vote, Party B 20%, and so on. Then you go out and run an actual survey. This test lets you look at the raw numbers and ask, do the actual observed responses match the model we expected, or have the voters shifted so much that we need to throw the whole model right out the window?
The second variation, the chi-square test for independence, is quite possibly one of the most valuable tools we have in the business world. It asks a hard-hitting question. Is there a connection between two entirely different traits in a population? Our sources use a brilliant example. Is the likelihood of having payment problems totally independent of whether you're a man or a woman? We set up a table based on what we'd expect if there was zero difference. Then we plug in the actual numbers. The gap between our expectation and reality tells us if there's a deeper connection, a hidden dependency that a bank or a business absolutely needs to act upon.
And finally, Part 6. A practical decision tool. Let's bring this all together. For you as a decision maker, this whole process is about a constant, conscious balancing of risk. Remember alpha, our significance level? If you are terrified of making a type 1 error, meaning you're scared of acting on a false alarm, you could set your significance level incredibly low, like to 0.1%. But you know what the cost of that is? Total paralysis. The test becomes so impossibly strict that the gears grind to a halt and you never take action when real changes are actually happening. On the other hand, if you set the level way too high, you risk running around like a headless chicken, completely overreacting to what is essentially just random noise and normal fluctuations in your data.
And that is exactly why I absolutely love this quote from the text we've been going through today. It nails it completely. Hypothesis tests must be understood as decision tools, not as mechanical truth machines. The statistics and tests we've looked at today, they are meant to guide your judgment. They give you a logical, highly structured framework to handle uncertainty and make tough choices. But they never replace your own understanding of the business or the core problem you're trying to solve. So with these tools in your back pocket, the next time you're staring down a data set that's pointing in a brand new direction, are you ready to take the calculated risk to challenge the status quo? Thanks for joining me on this explainer.